So now when we set these up in series with each other, and we think about like the voltage, well, this one over here, on this side, it's going to be seeing positive 20 volts. And on this side, it's going to be seeing 0 volts, this one is. But we don't really know what's going on in between there. What we know is that there's going to be some delta V1 across that first capacitor. There's going to be some delta V2 across the second capacitor, delta V3 across the third capacitor. And we can know the values of the C's, okay? And we know the values of the V's. But what we also know is that these all added up together has to come up to 20 volts. So we know this. Delta V1 plus delta V2 plus delta V3 equals delta V total. In our case, it's 20. Now, what about the capacitors? Well, we already talked about the fact that this equation works right here. So if we look at what is delta V? Well, we rearrange this and say that would be Q over C, right? So delta V1 would actually be Q1 over C1. And delta V2 would be the number of charges. Well, it's the same. We can say Q2, but I already talked about how a single charge here induces a charge here, induces a charge here. Q1, Q2, Q3, they're all going to be equal to each other. And Q3 over C3, and that equals the total charge over the total capacitance. But Q1 is equal to Q2, which is equal to Q3, which is equal to Q total. So if instead of just calling these Q1, Q2, Q3, we acknowledge that those are all equal, then we can just call them all Q. We'll just call them Q. And if we have Q over C1 plus Q over C2 plus Q over C3 equals Q over C total, we can take this, multiply the whole thing by 1 over Q, or divide by Q, however you want to look at it, and we will end up with this relationship. Unlike the case where we were in parallel, where they just add together, however many there are, you're just going to add them up. Over here, the reciprocal of the total capacitance, this is in series. The reciprocal of the total capacitance is just the reciprocal of each capacitance added together, 1 over C1 plus 1 over C2 plus 1 over C3, however many of them you may have, and that'll give you the total capacitance. Now, total capacitance is important for us to calculate for a variety of reasons. One of them tells us how much capacity we have to store charge. Another one is that when we are talking about capacitors, the amount of energy that is stored in a given capacitor, the potential, electric potential energy, is 1/2 capacitance times voltage squared. And so if you can get the total capacitance of the circuit, you can take that total capacitance, multiply times the total voltage of the circuit, square it, and get the total potential energy of that setup. Interesting, this looks a lot like 1/2 mV squared. This is a different V, this is voltage. Oops, and I'm writing above where you can see, this is voltage. But again, just like with 1/2 mV squared, where that was the kinetic energy of something that's moving, this is the potential electric energy of whatever charged up circuit that we have. So if we look again at that case where we said C1 is equal to 20 microfarads, C2 is equal to 40 microfarads, C3 is equal to 80 microfarads. If I want to know if that's what these are right here, and I got a total voltage there of 20, delta V equals 20. And I'd said before, what if these break down if you have more than 10 volts across any one of them? What we need to find out, is any one of these bigger than 10? Because if it is, we need to do something different or we're going to break one. So I need to look at the total capacitance. And I use that equation over there, that box. 1 over C total equals 1 over 20 plus 1 over 40 plus 1 over 80. And again, I could put times 10 to the minus 6 and all that, but ultimately, if I know I'm leaving everything in microfarads, my answer is going to be in microfarads too. And there's the inverse button on your calculator that I taught people how to use when we were talking about distance and focal length and all those kinds of things. You can use that here, or you can get common denominators. This would be 4 over 80 plus 2 over 80 plus 1 over 80. And that tells me that the total capacitance here, 1 over the total capacitance, is 7 over 80. I hope. Yep. 7 over 80, okay? Which means that the total capacitance is 80 over 7, which is 11 3/7 microfarads. Now, interesting to look at this and say, okay, well, before we just added them up, but now look, I got 20 microfarads, 40 microfarads, 80 microfarads. The total capacitance, putting those all together, is less than any one of them individually. That's kind of weird, but the reason to do this is because it increases or it decreases the voltage that any particular one of them will have to see. If I wanted more storage capacity, I put them in parallel. I can store up as many as I want. And I talked earlier about, I used to work, with these big capacitors. We used to work with those, and there were banks of like 24 of them together. And I've been in warehouses where the entire warehouse was filled with capacitors that were all banked together like that. But this is giving us, so this is 11, whatever that is, 0.428 microfarads. Now, if I want to know more about that circuit, well, what do I know? One thing that I know, that I erased, but I'll put back up here, is that C is equal to Q over delta V. So since C is equal to Q over delta V, if we want to look at, well, how much total charge can be stored in this circuit? Well, Q is equal to C times delta V. I know delta V is 20, and I know the total capacitance down here is 80 over 7, again, microfarads, times 20. These aren't coming out as nice numbers. I could have worked harder and made them come out nice, but I didn't. That's 1600 divided by 7, which is 228.57, something like that. I think 14. Yeah. Anyway, that's going to be in microcoulombs. Now, we talked about the fact that each one of these has the same charge on it. So the charge on this one's 228 microcoulombs, 228 microcoulombs, 228 microcoulombs. So now, again, using the same equation, but rearranging it again, I say, well, what's delta V? Well, delta V, for any individual one of those, is Q over C. And this is our Q for every single one of them. And therefore, if I want delta V1, I'm going to look at capacitor 1 and say it had 20 microfarads and be able to calculate a voltage on that. And so I do that, and I get that delta V1 is 11.4 volts. And that tells me right there, if the capacitor, if all that the capacitor can handle is 10 volts, this is going to blow my capacitor. Now, these volts all together, if I go delta V2, what's it going to be? It's going to be 228.57 divided by 40, which is going to be 5.7 volts. And delta V3 is 228.57 divided by 80 microcoulombs, or microfarads, and that is going to be 2.8 volts, 2.9, I guess we rounded up. And those three together all have to add up to 20, which they do. A little bit of round off there, but they need to add up to 20. So the total voltage is just adding those three up together.